Hi, my name is Liam Posher, and I am a student in W10. For the past few months, I've been working with Nathaniel Morgan, Travis Peary, and Jonathan Mace, looking at the implications of numerical operator mutation on differential systems. One thing we can specifically look at through this context is locally negative entropy production, also known as local entropy reduction. Now, specifically, what happens when a numerical operator acts on a differential system, as in when you numerically discretize a partial differential equation in order to solve it, is that sometimes via your discretion operation can introduce an effective numerical dissipative coefficient. What we're specifically doing in this work is trying to reproduce and comparing implications of locally negative entropy production in the context of having a physical dissipative coefficient for various forms, for example, heat conduction and viscosity. Now, why would one want to understand how numerical operators influence a differential system's behavior? Well, partial differential equations are highly influenced by what terms are turned on in that differential system. And sometimes a specific numerical operator can include new terms into that differential equation that are being solved numerically, such that an effective numerical coefficient could be ascribed to describe these new terms. And that's exactly what happens, for example, in upwinding and artificial viscosity. A new term to the differential system is being added implicitly to the solved numerical equation. So a correct understanding of how this dissipation occurs, which oftentimes this is what happens for stability, artificial viscosity, artificial heat conduction, include a term that smears out solutions in order to ensure stability. A correct understanding of how the dissipation occurs is very important to understanding the physics and the numerics of how certain solutions are created. Now, specifically, what we're looking at is how physical dissipative mechanisms influence a solution, and then we're trying to compare that to how numerical dissipative mechanisms can influence other solutions. And simply what we're looking at today is specific entropy density. Now, what equation are we specifically going to look at today? Well, today we're looking at the Euler equations for a hyperbolic differential system. By hyperbolic, we mean that information propagates causally, which is at the speed of sound in the Euler equations if you assume a linear perturbation to the system. And what we're doing, well, we're adding in addition to the Euler equations, which are all the terms that do not have yellow arrows pointing to them in the below equations here, is that we're including dissipative, irreversible, and non-hyperbolic terms such as viscosity, which is momentum diffusion, and heat conduction, which is energy diffusion. These terms are labeled explicitly in the equations below. Now, mass diffusion could be included for a holistic diffusive analysis, but is not considered for this application. One thing that's often done in mathematical and numerical physics is analyzing a differential system before we attempt to solve it. This is done to ease the burden of computation if solved numerically, or the burden of analytical rigor if the equation is solved analytically. Here we've assumed that we can non-dimensionalize the equation. We have introduced new variables that are non-dimensional for the independent variables x and t, space and time, and also new non-dimensional variables for the thermodynamic flow variables, which are density, flow velocity, specific internal energy, and pressure. Another thing we've also assumed is the ideal gas equation of state, which relates the pressure to density and specific internal energy. The ideal gas equation of state is just a simple closed form relationship between the various thermodynamic variables which may appear in our medium. In addition, gamma, which shows in this equation of state, is a ratio of specific heat capacities. For argon, which is a monatomic gas, which only has the translational degrees of freedom, gamma is 5/3. For nitrogen or oxygen, for example, which compose air and are diatomic, gamma is 7/5, which correspond to rotational degrees of freedom plus translational degrees of freedom that are available to that molecule, which compose that gas. Also, another thing that's being introduced is the non-dimensional energy ratios of Km and Ke, which correspond to a pressure divided by either the amount of energy that can be stored in a sound wave, which is per Km, or the amount of energy that can be stored in just the gas, which is rho naught E naught, which is the bottom half of Ke. In addition, once these variables are plugged in, these non-dimensional variables, I should say, we may also note that a Reynolds number and a Peclet number may be introduced, such that we have these apparent values for the Reynolds number and Peclet number showing up in our differential system. Combining all of these various forms of analysis together, we're able to write the full non-dimensional differential system that was discretized with a method of lines. The we have the conservation of mass, conservation of momentum, and conservation of energy, with the inclusion of the equation of state that closes the differential system. As one may have noted beforehand, that we had four unknowns, but only three equations. This inclusion of the equation of state allows us to relate the three thermodynamic variables amongst each other and replace one variable, typically the pressure, with the density and the specific internal energy in our differential system, such that we have three equations and three unknowns. Finally, our irreversible terms are highlighted in yellow, and you may note that they all involve either a square of a derivative or a second order derivative multiplied by a Reynolds number or a Peclet number. One of the things we use in our analysis was specifically the ideal gas law to close our differential system. Now that is one way that thermodynamics can help us analyze our differential system and allow us to look at specific variables which are of interest. Thermodynamics can also be used to analyze irreversibility in entropy production. So thermodynamic potentials, as described by Callan and in a slew of other works, may be used to transform a conservation of energy equation to a specific entropy equation. And so by using the relations all on the left, we have the Gibbs relation, which is also called another Euler equation, funnily enough, which is a relationship between internal energy and the entropy, volume, and specific, particle number. We may relate those thermodynamic potentials to each other via that equation, and also a fundamental equation for differentials, TdS equals dE minus P over rho squared d rho. We may plug those two variables into our conservation of energy equation such that we're able to get the equation on the right, which is a conservation of entropy equation. Now, an interesting thing to note is that in all our prior equations, we had no sources for mass, momentum, or energy, but here we have sources for entropy, which is very interesting. Now, one thing that may be noted is that we have multiplicative factors which are always positive to the left of our conservation equation, which is st plus u sx. Those multiplicative factors are ks, kt, rho, and e. Those things are always positive. We know that for a fact. There is no negative no negative density and no negative specific internal energy. Now, that conservation equation equals 1 over Reynolds number times some energy ratios times Vx squared, and x in this case refers to a derivative, a subscript x, I should say. And that's plus 1 over Peclet number times a second derivative of the energy. Now, one thing we can note is that the left-hand term in that right-hand side of the equation is always greater than 0. Something squared is always greater than 0. But we can also see that if we have a non-infinite Peclet number, that our right-hand term in that equation may be 0. And we can reformulate that equation again such that we can get the temporal derivative of entropy, which equals the flux of entropy plus its entropy production. Now, this is an extremely useful thing that we're looking at, such that we can try to determine how local entropy density changes as a function of space and time. The non-dimensional differential system shown in a previous slide is described via the methodal lines. The right-hand plot shows the numerical operator convergence as a function of the number of spatial points, and the bottom left shows this numerical stencil that was used to create the advance forward in time. So the whole reason we're performing this analysis is to look at the local specific entropy densities. Now, one thing you can note in the left-hand plot is that we can actually see negative entropy density in the blue areas and positive in the red. On the right-hand plot, you can observe the various viscous, conductive, and viscous types of solutions noted by the various values of the Reynolds number and Peclet number. And one thing you can note is that the viscous solution is always positive, the green curve. However, there's much difference in the structure between the viscous conductive, and the conductive entropy densities that are produced. Throughout this presentation, we've been able to show that locally negative entropy can be produced by certain terms in differential equations. We've been able to show this via the use of a physical dissipative mechanism. Now, numerical operators can introduce effective numerical coefficients which replicate the results that we've been able to show here with physical dissipative mechanisms as with the numerical dissipative mechanisms. This result may not be trivial or intuitive to understand due to the fact that oftentimes numerical operators, there's some applied mathematics analysis that must be performed in order to understand what is actually underneath the hood of an operator and how does it actually mutate and change the underlying differential system such that what is actually being solved numerically is different from what is actually being performed, what is thought to be performed via an analytic equation. And this is something that must be understood in order to fully understand how a numerical operator is able to change the solution and mutate that underlying differential system. Here are a list of references that were used throughout the making of this presentation. Thank you for your time.